Welcome back, everyone. So I'd like to pick up where we left off previously, which was introducing the idea that alcohols can undergo a substitution reaction with hydrogen halides, with HCl, HBr, or HI, in order to give the corresponding alkyl halide to whatever alcohol we started with. And this alcohol can be primary, secondary, or tertiary. I'm leaving these bonds unspecified here as to what they're attached to, could be to hydrogens or to other carbons. In all cases, you will wind up with the corresponding alkyl halide, corresponding meaning that it is the same number of carbons as the starting material, and also, of course, the same halogen as you're given in the hydrogen halide. Hydrogen fluoride will not work in this reaction because HF is a weak acid. The hydrogen-fluorine bond happens to be extremely strong, which is not true of the bonds from hydrogen to chlorine, bromine, or iodine. So those three hydrogen halides will work. The inorganic side product is going to be water. That's the fate of the OH group in the alcohol. Will wind up in a molecule of water. And the mechanism of the reaction depends on the structure of the alcohol that we start with. So if the alcohol is primary, or if it's methanol, the reaction will go by an SN2 reaction, just like we covered in the previous chapter. Okay, so if the alcohol starting material is primary, then the reaction will be by an SN2 mechanism, whereas if the alcohol we start with is tertiary, then it will react with a hydrogen halide by an SN1 mechanism. And these mechanisms are going to be very similar to what we talked about in chapter 6. There are going to be some details that seem different, but that's only because of the nature of the reagents. It's actually the exact same reaction in both cases. I hope to convince you of that as we go through this. So to use as an example of a primary alcohol, 1-butanol, like I could have used any other primary alcohol. If we were to react 1-butanol with HBr, we would get 1-bromobutane at the end, and of course also a molecule of water. You'll know whether or not you need to mention water by how the question's phrased. Again, watch particularly for OWL. They sometimes want you to do stupid stuff, so be sure to read the question carefully. In any case, one principle that's very important and a very general principle that we'll probably run into again going forward is if we're in an acidic medium, we can't ever make or use any strongly basic anions in our reaction mechanism. Those don't make sense in an acidic solution. So things like the hydroxide ion, alkoxide ions, NH2-, which is the conjugate base of ammonia, a very strong base, carbanions like CH3-. These species do not make sense in an acidic solution. They couldn't exist in acid. They would immediately be protonated. So that's why we can't simply have a bromide ion knock off OH- as our leaving group and make the alkyl bromide all at once, because we can't make OH- ion in acidic solution. OH- will not act as a leaving group in acidic solution. It's too strongly basic. You know from Gen Chem that OH- is a very strong base. So we need to do one step of preparation for the molecule before we can do our SN2 step. And that is that we need to put a proton on this oxygen so that instead of losing OH- as a leaving group, which again we cannot do in an acidic medium, we'll lose a neutral water molecule. Now, how can you know that we're in an acidic medium? You know by what we're given. You need to look at what we're given. We're given that HBr is there. And we know from Gen Chem that's a very strong acid, as is HCl, as is HI. So that's how we know. That gives us a clue that we're operating in an acidic medium, an acidic solution, and so we can't have any strongly basic anions around. So the first step involves using an HBr molecule to put a proton onto that oxygen. We've already said that alcohols can be amphoteric in a previous lecture. So we'll use a lone pair on oxygen to pull H+ off of HBr and make a bromide ion. You could even, if you wanted to, put the other lone pairs in the bromine. You don't have to, they're understood. We're pickier about that at the start of the term. But as we go on, we let such things fall through the cracks. Anyway, putting the proton in oxygen gives you the conjugate acid of the alcohol, which is this cation here. And now we can do our SN2 reaction. Now our bromide ion, which I think you'll agree with me, we just made a bromide ion here, and there's plenty of other bromide ions floating around in this solution. You don't need to worry. And why is it okay to have Br minus? We just said about anions in acidic solutions, so how can I have Br minus? Well, Br minus is not a strongly basic anion, right? Br minus is the conjugate base of HBr, which is a very strong acid. So Br minus is a terrible base. And so anions like that are okay in acidic solution, but only if they're extremely weak bases. So that would mean that they would be the conjugate bases of very strong acids. So Br minus, Cl minus, I minus, HSO4 minus. How about that one? The conjugate base of H2SO4, which is a very strong acid. So something like that, those are okay in acidic solution, but no very strong bases. And I think you have some idea of some species that are very strong bases, again, from your Gen Chem. So anyway, our bromide ion can now attack that carbon that bears the water molecule leaving group. We will break the carbon-oxygen bond and put those electrons in the carbon-oxygen bond onto the oxygen nucleus. This step does two things at once. It gets rid of the minus charge on bromine by using an electron pair to form a bond to carbon. And it also gets rid of the plus charge in oxygen by means of putting the electrons in the bond onto the oxygen atom and onto the oxygen nucleus. And so that gets rid of the plus charge. So that's where our water molecule comes from. And so in the end, we get our 1-bromobutane. And so again, this is a good reminder that the SN2 reaction is called that because it's a bimolecular reaction. There's two species involved in the rate determining step, the nucleophile and the substrate. So the concentrations of both of those species matter and will affect the rate of the reaction. Now, how do I know that this is the rate determining step? We say there's two species involved in the rate determining step. How do I know that's the rate determining step? Well, because it's the only step in the reaction, right? This step here isn't part of the SN2 reaction. And by the way, even if it were, which it isn't, but even if it were, one thing I can tell you is all proton transfers are always very fast. Any kind of Bronsted-Lowry acid-base reaction. Those steps are the fastest steps kinetically of them all. So this is the only step involved in the actual substitution reaction. And so that, by definition, must be the rate determining step. So this is a bimolecular substitution reaction. What if instead we had a tertiary alcohol? This is the one I mentioned in your class notes, 1-methylcyclohexanol. This will also undergo a substitution reaction with a hydrogen halide such as HCl, but now it's going to go by an SN1 mechanism because we have a tertiary substrate. Once again, we can't just lose hydroxide ion and make our carbocation directly, because if we did that, we'd be making OH minus in an acidic solution, and that's a no-no. That's not going to happen. No strongly basic anions in an acidic solution. If we were in a strongly alkaline solution, if we were sitting at pH 14, let's say, that's a different story. Then you can maybe contemplate steps that look like that, but not an acidic solution. And frankly, I don't know that we will even get to any reactions that go through strongly basic media. I could be wrong. We'll find out eventually, but I don't believe so. I feel like acidic medium is more common. So rather than losing the hydroxide ion immediately, we again need to protonate that oxygen in order to get that all-important molecule of water as our leaving group. Neutral water can act as a leaving group much more easily than hydroxide can. And in acidic solution, again, we have no choice. So this first step, again, isn't part of the substitution. That's just setting the species up to be able to undergo substitution. And so In the next step, we lose our water molecule. And that breaks the carbon-oxygen bond. The electrons in the bond go onto the oxygen atom, and we're left with a carbon atom that has 3 bonds and no lone pairs. So there's only 6 electrons around that carbon. And that's a carbocation. If you work out the formal charge on such a carbon, you'll find the charge is +1. And so that's the first step of the SN1 reaction. Remember, the SN1 reaction is 2 steps, and the first step is the slow step, the loss of the leaving group. And incidentally, this raises another question, which is, how could we have known that the first step is slow and the second step is fast? Answer, you can't have. There's no way you could have known that. That sort of thing needs to be determined by experiment. And this has been experimentally verified a long, long time ago. So we know that, in fact, by having proved it experimentally, the first step of the SN1 reaction is slow, and the second step is fast. The second step is our nucleophile attacking our carbocation. So we form that new bond. It'll be a new carbon-chlorine bond in this case. And so in the end, we'll wind up with the corresponding alkyl halide, namely 1-chloro-1-methyl cyclohexane, which would look something like this. And yes, we do form a molecule of water also, but we're mostly interested, as usual, in the major neutral organic product. So that's going to go by an SN1 reaction because we have a tertiary alcohol. Primary alcohols will go by an SN2 mechanism. And I just picked these 2 compounds as examples. I could have chosen any other primary alcohol or any other tertiary alcohol. I would suggest you do exactly that in your studies. Make up or look up another primary alcohol. You start small. What if we just added another methyl group on the end and made this 1-pentanol instead of 1-butanol? Do that. Work through the mechanism, figure out what the product will look like. Make up molecules for each other in your study groups. Oh, I guess there are no study groups. Jeez. Oh, golly. This is going to take some getting used to. Anyway, so certainly make up your own molecules and work through the mechanism and figure out what the product will look like. It's the best kind of practice I'm aware of in learning organic chemistry. For what it's worth, it's what I did when I was in college, way back before the earth cooled. So what if the alcohol is secondary, like isopropanol or something like that? Well, remember, secondary substrates are your intermediate cases. Those can go by either an SN1 mechanism or an SN2 mechanism. So in principle, if you put either one of the 2 down, it would be correct. In actuality, my expectation is that both would happen. Sometimes some molecules would go by an SN1 reaction, others by an SN2 reaction. The product you would get is the same either way, but you'd have both mechanisms happening. One other thing I wanted to point out in 711, even though you're technically not responsible for it, is being aware that phenol, which again is hydroxybenzene, we talked about it earlier, which is phenol will not undergo either SN1 or SN2 reactions with alkyl halides. So you can treat phenol or any substituted phenol with either HCl, HBr, or HI, and they will just look at each other. Nothing will happen. Oh, you might protonate the oxygen. You might go through that first step. But once you get as far as that, game over. Nothing further happens. And the reason is that the carbon-oxygen bond is so much stronger than in an aliphatic alcohol. So remember, the carbon attached to your leaving group in either an SN1 or an SN2 reaction must be sp3 hybridized. The carbocation carbon in an SN1 reaction is sp2 hybridized, but the carbon attached to the leaving group has to be sp3 hybridized in both cases for the reaction to go. Here, the carbon attached to what will become your leaving group is sp2 hybridized. As such, the carbon-oxygen bond is much too strong, and so no reaction. You will not get aromatic halides by treating phenols with hydrogen halides. Good. So let's move on next to oxidation reactions of alcohols. I think it's important for you guys to know something about redox chemistry, especially since it occurs all the time in living systems as well. So, through the miracles of modern science, We have some more material here now. So we're going to discuss now the oxidation of alcohols. And alcohols can be oxidized to carbonyl compounds usually, as I pointed it out in the class notes, usually undergo oxidation. And the condition for whether that will happen or not is we need to have at least one hydrogen directly attached to the carbon bearing the OH group. If not, game over. The alcohol can't be oxidized. But the product of the reaction is going to have a carbonyl group, C double bond O, and that's an oxidation reaction. O in square brackets is kind of a generic shorthand for an oxidizing agent. It means some oxidizing agent is used here. We'll get into specifics later. And that's exactly what we're going to do. So there's going to be a total of 2 particular oxidizing agents that you'll need to know about. One is going to be a strong oxidizing agent. The other one is going to be a mild oxidizing agent. And sometimes it will matter which oxidizing agent we use. Let's start with the simplest case of all, which we can dispatch in 5 seconds, which is if the alcohol is tertiary, like this one that we used just a moment ago. That's a tertiary alcohol. And to put it briefly, tertiary alcohols cannot be oxidized, period, full stop. There's no exceptions. And if you look at it, the reason is the carbon that bears the OH group over here has no hydrogens directly attached. And so as such, you could treat this or any other tertiary alcohol with whatever oxidizing agent you like. They will just look at each other. No reaction will happen. Tertiary alcohols cannot be oxidized. What about primary alcohols? With primary alcohols, we've got options. So let's use 1-pentanol for no other reason than I feel like it. That's a typical primary alcohol. You could pick any other primary alcohol you like in your example. And there's 2 different oxidizing agents to know about. Our mild oxidizing agent is PCC, which is short for pyridinium chlorochromate. You can find the structure of pyridinium chlorochromate in the book. I certainly don't care if you memorize it. But the thing to be aware of is PCC is a mild oxidizing agent. And so if you treat a primary alcohol with PCC, the product that you get will be the corresponding aldehyde. So an oxidation will occur, but the primary alcohol will get oxidized up only 1 notch, so to speak. And it will stop at the aldehyde and go no further. So you'll get the aldehyde with the same number of carbons as the primary alcohol you started with. So PCC oxidizes primary alcohols to the corresponding aldehyde. You'll notice I'm not using curved arrows here. So are we going to have to know the mechanism, Dr. Wass? Well, no, it's not in your book. We're not going over it. And frankly, I don't think we even could draw this mechanism even if we really wanted to. I don't think this is something that can be drawn with curved arrows like that. So you're not responsible for the mechanism of this reaction. But I did give in the class notes a step-by-step method showing how you can know what the structure of the product will look like given the structure of the starting material. And you might also want to be able to go the opposite direction. If you were given an aldehyde and told that some primary alcohol reacted with PCC to give that, could you draw the starting material? That would also be good to be able to do. So again, pyridinium chlorochromate is a mild reducing agent. It's because of the P in the PCC, the pyridinium. That species acts as a buffer, and you probably learned a little bit about buffers in Gen Chem. And so as a result, that makes the chromium in it, which is otherwise a no-holds-barred oxidizing agent, it makes it a milder oxidizing agent. So it will oxidize a primary alcohol up to an aldehyde, and it will then stop. It oxidizes it no further. Well, what if we treated our primary alcohol with a strong oxidizing agent? And the strong oxidizing agent that you will need to know about is generally called the Jones reagent. And you might see that written a number of different ways. you might see it written as chromium 6 oxide, CrO3, or you might see it written as H2CrO4, chromic acid, which if you think about it, it's pretty easy to see where we get H2CrO4 from. The difference between if you sort of subtract CrO3 from H2CrO4, I think you'll be able to convince yourselves that you get H2O. And so chromic acid is just what you get on adding water to chromium 6 oxide. This is an extremely good oxidizing agent, very, very strong. It's chromium in the +6 oxidation state. So that really, really wants to oxidize something. You may or may not see other reagents mentioned. You should get used to the reaction requiring acidic conditions. So aqueous acid is generally added. And they may or may not mention an organic solvent being used also. But if an organic solvent is also used, then we need to choose a solvent that will not undergo oxidation, one that's not going to react with our Jones reagent. That would be silly otherwise. Otherwise, our solvent would react with our reagent and mess up the reaction. So we want something that cannot undergo oxidation. And the usual choice is acetone, which has that structure. It's basically CH3, C double bond O, CO, CH3. CH3COCH3, that's acetone. So that's a good choice of solvent because acetone can't be oxidized any further. In any case, if we were to treat the primary alcohol with Jones reagent, now we would get not the aldehyde, but the corresponding carboxylic acid. And again, I've given you in the class notes a step-by-step method to go from the primary alcohol to the corresponding carboxylic acid. You basically just want to change the carbon that's in the CH2 of the CH2OH to a carboxylic acid carbon. So that's another level up in oxidation level from the aldehyde. And incidentally, Jones reagent also will oxidize an aldehyde to the corresponding carboxylic acid. So that will work too. That's our strong oxidizing agent. Just let me write that in. But you can do both types of reactions. You'll need to be aware of both reactions. Jones reagent is our strong oxidizing agent. It's much more reactive than PCC. And so it will oxidize a primary alcohol all the way up to a carboxylic acid, whereas PCC, pyridinium chlorochromate, oxidizes a primary alcohol to an aldehyde and no further. It stops at the aldehyde. Meanwhile, if you need to oxidize an aldehyde to the corresponding carboxylic acid, Jones reagent will do that for you also. One last one, let's consider now secondary alcohols. They are in many ways a relatively simple case also. So if we just did 1 pentanol, why don't we do here 2 pentanol? So, and the idea with secondary alcohols is quite simple. Secondary alcohols, regardless of which oxidizing agent you use, the strong one or the mild one, regardless, you will get the corresponding ketone. So you'll basically turn C single bond OH into C double bond O. Pretty simple. And so this is whether you use PCC or Jones reagent. It doesn't matter. If you treat 2-pentanol with PCC, you will get 2-pentanone, this ketone. If you treat 2-pentanol with Jones reagent, you will get the same ketone in both cases. That's the only possible oxidation product. So the only one where you have choices, so to speak, is with primary alcohols. And again, this type of redox chemistry is pretty important because you're going to run into it in your biology and biochem classes. Of course, we don't have chromium reagents floating around in our bloodstream. Chromium +6 is un poco carcinogenic. It's kind of nasty. So we have other sort of biological versions of those compounds that do these oxidations for us. Even in high school biology, you might have learned about NAD+ and FAD. They basically do the same thing for us that PCC or Jones reagent would do. So I'll just sort of leave that there as something that you'll no doubt cover in your biology classes. One quick point, I didn't skip 713. I wanted you guys to be responsible for that section as well. Not that there's really much to it. The main point there is that you can have more than one OH group in a compound. You can have a polyalcohol, so to speak, which I think you already knew. I certainly don't care if you memorize any particular ones, their names or structures. But at the same time, I'm confident that none of you would think it outrageous that you could have a compound that has multiple OH groups in it, 2 or more OH groups. And then finally, thiols are the sulfur analog of alcohols. So a thiol is simply RSH, where R can be any alkyl group, or it can even be a benzene ring. So the sulfur analog of phenol would be called thiophenol. It's a benzene ring with SH on it rather than OH. Not surprising that we can have this type of structure. Sulfur is right below oxygen in the periodic table. Unlike oxygen, sulfur can become hypervalent. So it's okay to have more than 8 electrons around sulfur. In the case of thiols, it is only 8 electrons around it. I can even draw it out. 2 of them are in bonds, and 2 of them are in lone pairs. So it looks very much like an alcohol. I would expect that the sulfur atom would be sp3 hybridized, and that we would have a bent geometry around that sulfur atom, just like we would have a bent geometry around the oxygen atom in water or in alcohol. So sp3 hybridization. Thiols stink to high heaven, and if you've ever smelled a skunk, you've smelled a thiol. The other place that they use thiols for a very different reason, because of safety, is in natural gas. When natural gas is provided to its users, and you might, I can't even remember if we have natural gas jets in our chemistry labs. They don't get used that much more often. Generally, open flames are frowned upon in an organic chemistry lab. But you might have dealt with natural gas jets or natural gas in other forms, and or in other uses, I should say. And you're aware that gas leaks are extremely dangerous. We need to find them before there's an explosion and people die, right? So you might even in the past have smelled gas, especially if you've used these natural gas jets. I would have you know, natural gas is actually odorless by itself. So what they do is add in a few tenths of a % of some thiol. I couldn't tell you off the top of my head which one it is, but whichever one it is, it's quite effective. You only need a few tenths of a %. And boy, you can smell that. That alerts you that there's a gas leak. Thiols are pretty easy to make by an SN2 reaction. If you took, for instance, 1-bromobutane. Oh, I'm sick of 1-bromobutane. Let's use 1-iodobutane. I don't think we've had an alkyl iodide yet. If you treated 1-iodobutane with sodium hydrosulfide, NaSH, then I anticipate you would get an extremely good yield of butane thiol and stink up the whole room, probably. So remember, this is essentially Na plus SH minus, and the Na plus is a spectator ion, right? That doesn't play any role in the reaction. Since the alkyl halide is primary, we would expect an SN2 reaction. And so I think it would be worth your while to figure out what that mechanism would look like. I'll even give you a bit of a hint here. I'll draw our hydrosulfide ion, right? So there's no Na+, that's not involved in the mechanism. Those alkali metal cations are spectator ions. They just float around and watch. But that would go by an SN2 mechanism and provide the thiol. That goes very readily. One last thing I want to mention about thiols is that they readily undergo oxidation to form what are called disulfides. And the stoichiometry of the reaction is such that you can take two thiol molecules, and in the presence of an appropriate oxidizing agent, this happens quite a bit in living systems, and we already mentioned some biological oxidizing agents, NAD plus or FAD. What you wind up getting is RSSR, not USSR, RSSR. And so that compound is what's known as a disulfide. And you can see that basically these two RSH molecules have come together and lost H2. And maybe I can even be a little bit more specific. These are all single bonds, of course. So that's what you would get. You can likewise go in the opposite direction. You can treat a disulfide with a reducing agent, just as O in square brackets refers to a generic oxidizing agent, H in square brackets refers to a generic reducing agent. You might have expected R in square brackets, but H in square brackets actually makes sense because generally if you're adding H's to something, which you would be doing here, then you're going to be doing a reduction reaction. So both directions are possible. This becomes super important in proteins where the amino acid cysteine is a thiol, has a thiol functional group. And so you can have some cysteine residue over here in some protein and some other one over here that might be 200 amino acids away. And you can bring these two together and oxidize them and form this disulfide linkage. And that's going to have profound effects on the structure of proteins. It's not something we're going to emphasize much. We'll talk about proteins also, but again, our stress is going to be on thinking of proteins from the perspective of an organic chemist. You'll get to all the biological function in your biology classes. But I should mention that if you've ever gotten your hair permed, gosh, I just wish I had enough hair that I could get it permed if I wanted to. But clearly, clearly that toothpaste is out of the proverbial tube. I don't have that option even if I wanted to. But if you have ever gotten your hair permed, it's these disulfide linkages that are involved. What happens is they treat your hair with a chemical that reduces all of these disulfide linkages and goes back to thiol functional groups. And then they shape your hair into whatever beautiful shape they want. And then they add something else that reforms those disulfide linkages in the proteins in your hair. And so it will then keep its shape that you've set it as. So that's that exact same chemistry. It's just redox chemistry. Other than that, that's basically it on chapter 7 on alcohols. So we'll move on to ethers next, since that's also going to be on your next exam. This chapter is very short, and even we're cutting part of what is already a short chapter. So although it sounds like there's 4 chapters on your next exam, really I see it more like 2 whole chapters and 2 half chapters. So it's really more like 3 chapters. So move on to that next. Other than that, have a good day, and we'll see you next time.